There is a predator in the fossil record that paleontologists have studied for over a century. Its teeth are enormous, its arms are powerful, its size is genuinely imposing. By every conventional measure, it should have been the most dangerous thing in its ecosystem. And yet, the evidence increasingly suggests that it was afraid. Not of other predators, not of rivals its own size, but of the animals it was supposed to be hunting. The prey, it turns out, was fighting back, and in some cases, in ways that the fossil record has only recently allowed us to see, the prey was winning. To understand how this happened, you have to go back to the late Cretaceous, roughly 75 to 66 million years ago, and into one of the most ecologically complex landscapes that ever existed on this planet. A world where the relationships between predator and prey had been evolving for over 100 million years, where the arms race between the animals that hunted and the animals that were hunted had produced solutions on both sides that even now we are still trying to fully understand. The central case study is one of the most famous ecosystems in paleontology, the Hell Creek Formation of what is now North America, and the predator at its apex, Tyrannosaurus rex, has become so culturally dominant in our imagination that we have perhaps stopped looking at it clearly. Because when you look at it through the lens of what its prey could actually do, the picture that emerges is genuinely unexpected. Let's start with Triceratops. 3 horns, a massive frill, a body weighing up to 12 tons.
The frill was thought to function as a shield, protecting the neck from biting attacks. But a series of studies over the past 20 years have substantially complicated that picture. Paleontologist Andrew Fark and his colleagues analyzed injuries on Triceratops frills and found a striking pattern. The frills show healed wounds, marks consistent with horn impacts, but those wounds came primarily from other Triceratops, not from predators. The horns were being used against members of the same species, almost certainly in competition over mates or territory. Which raises an immediate question. If the horns evolved primarily for intraspecific combat, why were they so well positioned to threaten a predator approaching from the front? The answer may be that the two functions were never separate. Evolution rarely invests in the single use. A weapon refined through millions of generations of competition with rivals is also, by necessity, a formidable deterrent to anything else that approaches from the same direction. And T-Rex did approach from the front. We know this from bite marks. Paleontologist Gregory Erickson's work on T-Rex feeding behavior shows evidence of the animal attacking Triceratops from multiple angles, but the anterior approach, directly toward those horns, carries a risk that is difficult to overstate. A Triceratops horn could reach approximately 1 meter in length. The animal could deliver a charge at speeds estimated between 15 and 25 kilometers per hour. A predator absorbing a direct horn impact to the face or neck would sustain injuries that, in a pre-antibiotic world without any medical intervention, would very likely prove fatal. And we know that T-Rex individuals were frequently injured.
Examination of healed injuries in T-Rex specimens shows bite marks from other tyrannosaurs, broken and re-healed ribs, damaged vertebrae. Some individuals survived injuries severe enough that they would have been incapacitating for months. Whether any of these injuries came from prey animals is difficult to determine, but the fossil record makes one thing clear: being T-Rex was not safe. But Triceratops is only the beginning of this story, because the phenomenon of dangerous prey was not limited to one species, one ecosystem, or even one era. Go back further, 165 million years, to the Middle Jurassic, and you encounter Stegosaurus, an animal whose defensive equipment is, in some respects, even more remarkable than anything Triceratops possessed. The tail spikes of Stegosaurus, the Thagomizer as it has been informally named since a 1982 Gary Larson cartoon accidentally gave paleontologists a useful term, were not ornamental structures, they were weapons. A 2008 study by Miriam Carpenter examined a tail spike from a Stegosaurus that had been broken and partially healed, suggesting the animal had used it in life with enough force to fracture it. More significantly, a partial pubic bone from a large theropod discovered in the same formation shows a wound that matches a Stegosaurus tail spike almost exactly in size and shape. The wound shows signs of infection. The predator likely died as a consequence of this injury. The prey killed the predator, and the fossil preserved it.
This is sometimes called the evolutionary arms race, but that framing can make it sound linear, as if predators were always winning until prey caught up, or vice versa. The reality is considerably messier and more interesting. Both sides were simultaneously gaining and losing advantages. Generations of prey that developed better group cohesion changed what hunting strategies were effective. Predators that developed better ambush techniques changed what vigilance behaviors were worth maintaining. The relationship was not adversarial in a simple sense. It was co-evolutionary. Each side was, in a very real way, building the other. And here's where the picture becomes genuinely strange, because the most dangerous prey may not have been the largest or the most heavily armed. Hadrosaurs, the duck-billed dinosaurs, are not typically cast as threatening animals. They lacked horns, they lacked spikes, they were obligate herbivores weighing up to 3 or 4 tons. They appear at first glance like ideal prey, numerous, nutritious, apparently defenseless. Except that they weren't defenseless in the ways that matter most. Hadrosaurs possessed some of the most sophisticated sensory systems of any dinosaur we know of.
Their crests, the elaborate bony structures rising from the skulls of species like Parasaurolophus, have been analyzed extensively, and the current leading hypothesis is that they functioned as resonating chambers, producing low-frequency calls that could travel significant distances through dense vegetation. A 2012 study by David Weishampel modeled the acoustic properties of Parasaurolophus cranial crests and found that they were capable of producing sounds in the frequency range most effective for long-distance communication in forested environments. These animals were calling to each other continuously over large areas. And the group itself was dangerous in ways we are still trying to quantify. A herd of hadrosaurs weighing 3 to 4 tons each, moving collectively in response to a threat, represented a physical force that even a large theropod would have needed to consider carefully. Trampling injuries in large theropods are difficult to confirm from fossil evidence alone, but the mechanics are straightforward. An animal that triggers a stampede it cannot evade does not necessarily survive that encounter. What the fossil record is increasingly revealing is that the predator-prey relationship in the Mesozoic was not the simple hierarchy we once imagined. The predators were extraordinarily capable, but the prey were not passive participants in their own consumption.
They were active, intelligent, socially complex animals that had been shaped by hundreds of millions of years of exactly the same selective pressures that shaped the predators. Personally, I find something deeply compelling about this. The narrative of the apex predator as the ultimate expression of evolutionary achievement is a human story. We imposed it on the fossil record because it felt intuitive. The reality the fossils are showing us is more interesting. A world where every species was simultaneously predator and prey in some sense, where the defining feature of the ecosystem was not dominance, but negotiation. A constant, violent, generationally slow negotiation between what hunts and what is hunted. And in that negotiation, the prey were never just victims. They were participants. Sometimes the participants with the better argument. If the hidden complexity of prehistoric ecosystems pulls at you the way it pulls at me, the next investigation follows naturally from this one. Because the question of how prey defended themselves leads directly to a deeper question. How intelligent were these animals really? What was happening inside the mind of a hadrosaur calling across a Cretaceous forest? What was happening inside the mind of a Triceratops deciding whether to charge? That investigation is already waiting, and what the science has recently uncovered about dinosaur cognition will change the way you see every fossil you have ever encountered.